pre-trained language models. You select any one, let's say this digital bot, and you select this one, and you can know the syntax from here. That means how to use that that language model in your program, or you can come here and here you can get what is the syntax, how to call this. Now it may happen that these models initially may not give good result because these models, though they are trained on a huge amount of data, this data may not be of your domain. For example, these models are trained on news data set. Fine. Now you have to do this text classification on movie review. There is a domain difference in these two tasks. So you have to fine tune it on your annotated. Then you can see that using very small training, you can get better result than your previous models. So in our task, we are doing here uh, grammatical correctness checking. So similar task here we are selecting. That means here we are selecting. You can say that we also our task is to check whether a sentence is grammatically correct or not. So it is similar to this text classification. This token classification is, for example, the input in the input sentence for each token, we are getting it labeled. So for QH tagging or named entity recognition, we can use this token classification. For question answering, this is question answering, you can use there are lots of 10 models. For text to text generation, here are some similar problems like missing translation, the text to text generation. Your summarization is also text to text generation. There are lots of specific models like translation is also there. So basically, we are using here a model, any model you can use for text text classification. Here we have used basic BART base. So first here in this code block, we have checked whether your GPU is available or not in your Colab. So you can do what you can do in the runtime. We change the runtime to GPU is already GPU there, and now save it. And now I am running this way. So if GPU is available, then you will get similar type of result. Based on the GPU available, this output may change. Now, what to use these language models, what you have to do, you have to first install this transformers package. So you run this package using pip install transformer. Now you have used some relevant package. Here you have to download the data set. So we have to install the wget, and using this wget, we download this specific data set. Okay. In your case, you may use some different data set. This data set may be available to you, so you don't have to use this code snippet. But if you have to download the code, the data set, then you can use this code. And here you can see the downloading. Now we will get this zip file here. And now I am unzipping it. So downloading data set. It's downloading. It is unzipped. Yes. This one. Inside this Cola public, this is your file. You can see the dev set in domain or domain training data, dev data. You can see the dev data. What is the data structure? So this is CSV file, TSV file, the sentence and the label 1 and 0. 1 means grammatically correct, 0 means correct. Now I am parsing the TSV files using pandas. In your case, it may be not a TSV file, it may be a text file. In that case, your pre-parsing will be different. So basically, this is a table. From here, we will only consider the sentence and this label. Now we have extracted in the sentence, we have extracted all the sentences list and the labels is the label list, corresponding label list. Now, what you have to use? So I am using this BART based uncased. This is a pre-trained language model trained on uh, different. It is generally trained on Wikipedia data and used dataset. So what you have to do, you have to call select the model. You select the model from this from here. You text classification. You use any model. The, all will design for the same task. But the problem is that your syntax may be different. Your the backbone, because the architecture is different, there may be some minor change. Okay, so if you select any model, it will consider two things. You will select a tokenizer and a model. Okay, so what is the input type of in the model? So first task, our task is to load the tokenizer. So the syntax is from transformer input BART tokenizer. What happened? The BART has its own dictionary. Okay, the BART has its own tokenizer. For example, in your previous task, when we tokenize a sentence, we tokenize based on the space. But here, BART has its own tokenizer. It follows word piece model. So, for example, if one word is there which is not present in the BART dictionary, so BART will split it, okay, based on the tokens available in its dictionary. So here that tokenization took place. So on how it select which tokens to split or how to tokenize based on this model. In this model, there is dictionary, and based on the dictionary, it will tokenize. So do lowercasing is true. Why? Because it is BART based uncased. It is trained on the on the data where all the data are lowercase first. So if you want to stop this lowercase, in that case, you have to use BART based case. There is also a model available. Here it is uncased, but this is another variation of this model is available. You can get all these models here. It's about large uncased. Then so after that, you can see that here I am just checking how this tokenize work. What is the output of this BART tokenize? If you run this code, so this sentence contains all the sentences. So sentence 0 is the first sentence. Somebody just left. Guess who? Now, based on the after doing the tokenization using the BART tokenizer, you will get this type of list. You can see, you can check. See here in this sentence, you can see that here the sentence is neither von Karajan's recording of Beethoven's something. So here this token is not present in the BART dictionary. So what BART does, but split this token into two parts, Kara and Jan. This double hash indicates that it is not the actual word or token in the actual input sequence. It will be added to the previous token to make the original one. So, for example, here also it has splitted the word into multiple subwords, subtokens. Fine. So, if you have to get the original sentence based on this clue with a double hash, you can see you have to understand that this is not a proper word. You have to aggregate all with this with previous token to make the actual and corresponding IDs in the vocabulary in token IDs using this tokenizer.convert token to IDs. This will convert all the tokens to corresponding IDs. So now this tokenizer.encode plus will encode the sentences in that format such that it will fit to the model, BART model. So BART model considers two things as input. One is this token ID list and another one is attention mask. So attention mask indicates which are valid token and which are padding tokens. This may vary based on this input formatting may vary from based on the model your pretend language model you are using. For example, in case of Robota, I guess that I think that this attention mask is not used. Fine. In that case, there may be some other parameter may be used, another thing, another structure they can feed to the model. But here for BART based uncased, you have to feed two things. One is input ID, another is attention mask. And these two things you can get from this encode plus function, tokenizer encode plus function. But it will take as input, it will take the sentence and the additional special tokens that means it is true. So what, and there is some change in the input also. These two special token added to each sentence. One is CLS and the other one is separator. This CLS token added in front of the sentence. For example, this is the sentence. So CLS will be added before this neither to indicate the start of a sentence, and this ACP is a separator token, so it indicates the end of the sentence. After full stop, there is a separator. Fine. In case of two sentences, you consider as input. In that case, CLS sentence one, separator sentence two, plain separator. Fine. So the ID of this separator token is 102. That's why you can see that in case of this is the input, our friends won't buy this analysis. Let's so let's say this is a your sentence. Somebody just left, guess who? So here after this encode plus function, I have printed the values. That's why if you can see, I am printing the sentence 0 here. Here, here the tokenized sentence is this sentence set, and the token ID is 8307 to 1012. 1012 is the ID for full stop. And but after using this tokenization and include plus, what we get is CLS token is added in front of the sentence. So 101 is the ID for CLS token, and 102 is the ID for separated token. So whatever sentence you feed to a bot, you can use this function or not, but you have to add a CLS token in front of the sentence and a separate token in the last of the sentence. Okay, this is the format in which bot takes input, and these zeros are the padding token to fix the sentence length. If because in case of in let's say in batch size there are 5 sentences, so it will consider all the sentences in a fixed length. That's why padding is required. And this attention mask will indicate one for valid tokens. So from 101 to 102 it is 1, and after that it is 0 to indicate the they are padding tokens, they're not valid tokens. So you can check what is the maximum length of sentence in your batch, and based on that you do the padding. Then you know that we use mm, uh, data loader to load the data. So here you use tensor dataset and data loader and tensor dataset. Here we split the training sample and validation sample, and here you use data loader. Here you then data loader take the input train data loader sampler and the batch size. Then we, after getting the data set, now we are designing the model. So the model will be same name BART plus Suncrest. You you cannot use two different model in tokenizer and in model. You have to use same model name, because the tokenization is this model, how the input will be taken is depends on the tokenizer. So this should be matched, else it will be not work. Okay. So the syntax may be different. You can use different other classes also, like auto model. But here, as we are using BART for sequence classification, so we are using this BART for sequence classification class. So what it will take? It will take the whole sentence as input, and it will predict the class. Here number of levels should 2, as we have 2 classes. You can change it based on your class. And here we are just inputting the GPU. Now BART has a specific in the large language models. It has 12 layers. Printed the label, the layers. You know it is based on this that paper attention is all you need. That all we need. Basically, it has a self attention model, and with that there is a mm, self attention, and then there is a fully character layer. We can see that dot self attention and then linear layer. Then again layer normalization, then again part attention, and then linear layer. Here I just printed the parameter size. Now here you're defining the optimizer, and generally we use Adam, but for BART it is mentioned in the paper that we have to use it is Adam W. Okay, so basically W means the waiting decay. So based on the epoch, we are changing the learning rate. Now we defining some hyperparameters like epochs. Basically, if you do not use pre-training, that if you use typical model training, in that case, the epoch may be more maybe high. Maybe you have to epoch, we have to run this code for 20 or 30 epochs. But in case of BART, if you use pre-training and fine-tuning approach, then maximum 4 to 5 epochs is enough. So here we have used epoch 4. The total number of steps equal to the number of data loader into number of epochs. Basically, it is the number of batches into number of epochs. This learning rate scheduler is indicates what is the schedule. What is the schedule in which we change the learning rate? These are not required. This indicates how much time it will take to complete an epoch or step. This function is required. It calculates the accuracy. One is predict from the output. It will after the output of the softmax in the last layer where we classify the classify the outputs. This is the labels. There you use after softmax. We get the maximum, the level with maximum probability. This NP or Rmax will be the same thing, and this is the actual level. Based on this comparison, we can calculate the accuracy. This seed is required to get the same result all the all. Each time we run the code, we get the same result if we use this seed value, fix the size seed. Now in the training code, we for each epoch, we select the model to train. It indicates that we are right now we are in training mode, so we have to change the parameters to update the parameters. Now for each step, the train loader for each batch, what we will do, we will, that means you are selecting, let's say your batch size 40. In that case, you are selecting 40 sentences. You get their input IDs, input mask, and the actual level. Then you call the model. The model, what it will do, it will consider the sentence. Then it will get the evident representation for each token. Then it will select the embedding of the CLS token. And the embedding of the CLS token is into a multi-layer perceptron, which will predict the class, whether it is 0 or 1. So normal BART, what it will do, normal BART gives us embedding of each token. But when we have used this BART for sequence classification, that means on the top of this BART, there is a class multi-layer perceptron, a linear layer. So what is the input of the linear layer? It takes the input as the embedding of the CLS token, and it predicts the class. Then we calculate the loss and we train backward. This is the back propagation. This is to clip gradient, means to fix the gradient. This to prevent the exploding gradient problem. And this here we are changing, we are updating the parameters, updating the learning rate. And then we have validation. In the validation, here we will stop the gradient checking with torch of no grad. In doing the same thing, and based on the accuracy, we are saving the model. This way, you can train your BART model. One thing.
Hello, Alapan.
Yes, yes.
So, since we're fine tuning, it will only propagate till the last multi-layer perceptron layer, or how much will?
It depends. You can change it. You can change it whether you train the whole model or you change on you train only the classification layer. It's up to you.
Okay, where have you mentioned it here?
Because here I have used this part for sequence classification.
Okay.
I have used this one. I think here there is no convention to freeze the sum model. Okay, but if you use direct but from pretend, you use the, if you do not use this bar for sequence classification, in that case you can use the, you can freeze the model.
Okay. Oh, here, so it automatically freezes the other layers.
Yes.
Okay.
There, and after that there are some how the training and validation loss is changing. Then some getting the accuracy on the test data set. In the test data set also you have to do the tokenization, you do the tokenization, and then there is. Okay, in the next class is on, it will be happening in the class. So I think in the Thursday and Wednesday or Thursday, Wednesday, I guess. So on that class, I will try to code how can I can freeze the some the pre-trained language model and train only a specific layers and get the output yields.
So can we use this transfer learning for the assignment also?
Mm, you can, but I have already mentioned in the assignment to use bi-listing.
Yeah. Yeah.
You can in the comparison you can show that using BART we are getting this type of output, but you have to implement the bi-listing.
Okay.
Because if you use BART, then the problem will be very easy. The code will be very easy. You just have to BART and get them. Even without using any training, fine tuning, you will get better result than bi-listing, I guess.
So when we are doing this transfer learning, we can't use the Lightning library to do all the training for us? We have to write their own training loop.
Yes.
Okay.
Tell me again.
So while using this transfer learning, we are loading pre-trained base. So how to use PyTorch Lightning with this, or should we use that right training loop ourselves?
We have to write the code for the training loop. You have to code it.
Okay.
That one is much more abstract, right? That PyTorch Lightning.
Yeah.
In the next class, maybe we will show some comparison of the output using some without fine tuning, or you can use some large language models.
So sorry, one more doubt.
Hmm.
So while calculating this accuracy, you're moving the label CPU, no? So when we make the model in the evaluation mode, does it go to the CPU automatically?
If you this variable will be on the CPU. Okay, the CPU.
Okay. All right.
In the next class, maybe we can code some this pre-training and fine tuning in much broader, more elaborate form. That class will happen in the class. Next Wednesday. The class test is on Thursday, right? Thursday is class test.
I think it was mentioned 30 or 31.
If the class test is on Thursday, then Wednesday we try to code that fine tuning or elaborate in the class.
Okay.
Okay then.